Okay, so we looked at the graphs then, and now let's look at writing some equations of lines. So we can graph lines, but we need to write some equations of lines. And as I said earlier, mainly what we're doing in this one is not so much just equations of lines, but actually looking at some applications or some word problems. Okay, so before we get into the word problems then, let's just put a couple things on the board here. So y equals mx plus b is always our go-to, but it's not always the equation or the form that we start off with. So the other form of the line that we see is called point slope form of the line. And point slope form of the line requires, so if we have our slope and a point, just exactly what it says there. So if we have m and x sub 1, y sub 1, then point slope form looks like this. Y minus y sub 1 equals m times x minus x sub 1. So when we're doing our word problems, our applications, and we've got to plug these guys into a form to get the equation of a line, this is normally the guy that we're going to go to. So definitely going to use this, but let's talk about the slope for a minute more. And again, somewhere before, in order to get to this point, you've seen slope, but now I'm going to change it up a little bit. So we're going to call it slope still, but I'm going to give it its more proper everyday name, which is average rate of change. So whenever you're being asked to find average rate of change, basically they're asking you to find the slope. But this is more the way that you're going to be asked if you're doing a word problem. So remember that slope equals m, and that if we're in our normal algebra classroom, then it would have been y's over x's, y sub 2 minus y sub 1 over x sub 2 over x sub 1. But when we switch it over to average rate of change, the formula is still exactly the same, it just looks a little bit different. So instead of the y's, we're going to remove those and we're going to bring back the f of x form. So it's going to look like this. F of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. Same formula, different notation, different name, all the same. So let me give you an example, just an example that I've made up here. And let's, something to be clear on, when we work through examples that are in algebra class, then we'll use fractions to note like our slope, like you saw in the last little lecture. I used fractions, I didn't use decimals. But if we're going to do a word problem that's in the real world, if the numbers don't come out nice, then we're certainly able to use decimal format in real world examples, okay? So for the real world guys, decimal is okay, but otherwise normally want to try and leave things in fraction form. Okay, I'm just gonna make one up. So let's say the population in Barfville is seeing a linear decline. The population in, let's go 1990, was 41,500, and in 2005 the population was, let's go 26,100 people. Okay. Find the average rate of change. Okay, so maybe the reason the population in Barfville is seeing a decline is because of the name of the town, Barfville. Who knows, does it smell, is it disgusting? We don't know, but yeah. So they're seeing a decline in population. So they give us two pieces of information. The population in 1990 is 41,500, and in 2005 is 26,100. So they are not asking us to go directly to the line or anything. They're kind of doing this part A, or I am, part A, B, C. The first part is to find the average rate of change. So we're looking at this over here. Now, one thing to keep in mind when you're doing a word problem that deals with population and time. Time is always going to be your X variable. Okay, so time, which sometimes gets used as your T for your T variable, but it is also your X variable. So if we were to draw this out as if we had 2 points, the points would be in 1990, the population was 41,500. In 2005, the population is 26,100. Okay, so the time is always going to be your X coordinate, and then the population will be your Y coordinate. So if we want this average rate of change, or we can call it slope, or we can just call it M, average rate of change, we need to subtract the Y values, or the F of X values, the answers, which is the population, up top. Okay, now remember, order matters. So if this is the first, and this is the second, then it should go the 26,100 minus the 41,500. And then on the bottom, it should go the 2005 minus the 1990. Okie dokie. Now, okay, like I said, if you're like, oh, I don't want to do this by hand, or I just want to use my calculator, the 26,100 minus 41,500 is negative 15,400, and we're going to divide that by the difference in the years, which is 15. And when we divide by 15, we get negative 1,026.7. But this is a word problem, so we need to figure out how to label this guy. So that's what our slope is, negative 1,026.7. But now remember that population is up top, so it's going to be people per, and time is on the bottom, so people per year. So what it looks like is about 1,027 people are leaving Barfville each year. Okay, 1,027 people are leaving Barfville each year. Okay, so now what if I asked you to give a model for this linear decline? So that's the way the question is going to be asked. Sometimes find the linear model. And basically what that means is write the equation of the line. Write linear equation. Okay, and that's where this guy comes into play. Okay, that's where this guy comes into play. Alrighty, so let's say we have to use 1 point. So let's say that we're just going to use this first point just for the heck of it. It doesn't matter, you can use the other one if you want. But let's just say we're going to use that one. Using point slope form of the line, we're going to go y minus y sub 1. So our y is that y sub 1 is that 41,500. So we're going to go y minus 41,500 equals, and then we're going to do m, which is our negative 1,026.7, and then x minus our x value, which is 1990. Okay. Alrighty, so now we need to multiply in with that 1990 to figure out if we get there. And again, as we're dealing with decimals, we can use our calculator. So y minus 41,500 equals negative 1,026.7 x. Those will turn into a plus, and we'll do 1,026.7 times 1990. And I get 2043133. And then last but not least, we're going to add our 41,500. So we have y equals negative 1,026.7x, and then let me add 41,500. So plus 2084633. 2084633. Okay. And there's our line. Okay. So we've got our y equals mx plus b, but there is one thing that we want to pay attention to, and that is the domain on this guy. Now, normally lines don't have any issue with the domain, but because this is a real world example, there may be domain situations. Okay, so there may be domain issues. And in this case, Barfville probably wasn't founded in the year 0. So it's very possible that the city of Barfville wasn't actually even a city until 1980. So what you might see is they give a limited domain where they say, let t, or x being time, start in 1980. So there you might see something like domain equals 1980 to infinity. Okay, so with the assumption that Barfville's domain starts in 1980 and heads towards infinity. Now, again, it's real world, so is it going to go for infinity? No, but at least that gives us a limiting. So if you were interested in 1975, you would not be using Barfville's line, because Barfville apparently wasn't around, or at least wasn't a city until the year 1980. Okay, so a little bit of a limitation on the domain. And you will see that in these word problems, where they're going to set the domain and tell you it doesn't work for all x values, it only works in this particular situation. Okay. All right, so that's what you're looking at for the equations, or sorry, not the equations, the linear functions. So some graphing and some word problems, okay, but that should keep you going.